really began the modern era of theoretical physics that should provide the stumbling block to further progress toward a unified theory of all the forces of nature. Why? Because general relativity is the theory for gravitation. Gravitation is not explained by particle physics. It's not explained by quantum mechanics. See how that's an issue? Because there's the four fundamental forces of nature. Three of them are unified. Gravitation is not unified with those three. So what's going on there? What's the bigger theory that can hopefully bring it all together? We don't know. We only have a candidate, and it's the time, and it's the that candidate is superstring theory. Tweaking. What's tweaking? What do you mean? In many ways, the force of gravity is extremely weak. It is the weakest one of the four. It is the weakest one of the four. We've talked about how the four fundamental forces are quite different from each other. Gravitation and electromagnetism are felt and known more universally. Like, we're all aware of gravitation, we all feel it. Electromagnetism, I mean, if you get a shock, of course you feel it, right? We feel charge and forces on a charge, etc., etc. Strong nuclear force and weak nuclear force, of course, these are more exotic things that we don't exist in that scale so much. They are sort of things that are happening at much smaller scales, at quantum scale. So they're much more of a quantum contribution to our understanding of this world, if you will. Gravitation is, of course, the general relativity or a classical contribution. It's felt at large scales as well, right? Large scales, hour scales, things like that. But the problem is that gravitation is not explained. Nowhere in quantum mechanics are we getting a particle nature of gravitation, okay? So most material bodies are held together by electrical forces between atoms, which are many orders of magnitude stronger than the gravitational forces between them. But despite its weakness, gravity has a perplexing nature that seems to resist attempts to put it together with quantum theory. So it's true that electromagnetic force is stronger than gravitation, but they're not the same. So remember how gravitation is an always attractive force. Always attractive. Two bodies with mass will always be attracted to each other. Electromagnetic force is stronger than the force of gravitation, but it is sometimes attractive and sometimes repulsive. Like charges are repulsive towards each other and opposite charges attract. So gravitation and electromagnetic forces, these are not the same. They're not the same, okay? They're not the same. One is a lot stronger than the other, but first of all, both we're familiar with, and one of them is very universally present, which is gravitation. I mean, electromagnetism is present too, but what kind of, for example, we talked about large scale structure, right? What is sort of really important in cosmology is what's happening in the universe at a large scale. And at that scale, gravitation is a player. It's a very important player. So we would like to understand it better. We really would. And so it's a bummer when it's not explained by quantum mechanics and particle physics, okay? Einstein's general theory of relativity is a classical theory in the sense that Maxwell's equations of electromagnetism are also classical. They involve entities that are smooth rather than discrete and describe behavior that is deterministic rather than probabilistic. So once again, classical will be smooth, quantum will be discrete. Classical will be deterministic, quantum will be probabilistic. Those are the differences. But also, the gaps are there as well. Classical cannot explain certain quantum things, and quantum cannot explain gravitation. That's the issue. So on the other hand, quantum physics describes a fundamental lumpiness. Everything consists of discrete packets or quanta, Likewise, the equations of general relativity allow one to calculate the exact state of the universe at a given time in the future if